All right. So we have just talked about the structure of power electronic system, including main circuit, control circuit, feed-forward, feedback. I know some students still have some puzzles in understanding feed-forward, feedback. We'll touch that later on for more details. Maybe at that time you will have better understanding. All right. Since we are dealing with conversion and control of power, then it's going to be essential that the power converter itself does not consume too much power. Okay. Ideally, we would expect that 100% of input power will be all transferred to the output side after conversion. And that is related to another terminology which is called efficiency. Okay. As we can see, efficiency is defined as the output power divided by input power. And we always want a power converter to achieve 100% efficiency. Okay? Because high efficiency leads to low power loss within power converter. And when the converter itself does not consume too much electric power, then the converter design, like the volume, weight, and size of the converter can also be made much smaller. Because one reason, in the future we'll have the understanding, one reason that we need to build a power converter to be having some size, some big size, big volume, and higher weight, is that the converter needs to handle those power losses. If there is a lot of power loss in the converter, we need to handle those loss, because power loss needs to be handled in terms of heat. We need to transfer that heat out of the converter. If we don't have that handling, if we don't have that handling of the heat generated by the power loss in the power converter, then the temperature of the power converter will rise up. And when the temperature rises up, it finally will be exceeding the tolerated temperature a power converter can handle. Okay, like for semiconductor device, for semiconductor components, usually the maximum temperature it can handle is 150 degrees Celsius. 150 degrees Celsius. If you don't handle that heat generated by the power loss, then the temperature will rise up, will exceed that level, and it will be destroy the power semiconductor device. The converter will fail. Okay, so in order to handle that heat, we need to have kind of arrangement of size. Okay, in order to kind of radiate the heat out, we need to have larger surface of the device. Sometimes if the surface is not large enough, then we need some heatsink, an extra heatsink attached to a power semiconductor device, because that heatsink will give you much larger surface area to help you to dissipate the heat. So therefore, larger size to dissipate heat, maybe with the help of the heat sink, that makes the volume and weight and size of power converter larger. Okay. So if you are able to reduce power loss, so then that means the heat you need to handle is going to be smaller, and therefore the size and weight of the power converter can be made much smaller. Okay, so when you see the power adapter, okay, like this, and this is a power converter. Many of you know there's power converter because you want to transfer AC power to DC to supply the computer. And in the past 20 years, the size of the power adapter for laptop computer has been reduced dramatically. 20 years ago, I know you were very young 20 years ago, you would be able to see the power adapter for a notebook actually is quite big, like this, light green. After 20 years, it has been reduced to much smaller volume and weight. And one of the reasons is that we were able to improve the efficiency. One of the reasons we were able to improve the efficiency of this power converter dramatically. So therefore, the heat we need to handle in the power converter is going to be dramatically reduced. And therefore, the size of the converter, size of the adapter can be reduced. So right now, this is this adapter is able to handle a power of 65 watts. 65 watts. That is very often enough. Always, for most of the laptop computers, this is really enough. It has very small size. Okay, so that's about efficiency. Okay, and in order to achieve high efficiency, the devices that we're using in the power converter is also are also very different from, quite different, I would say, quite different from the devices we usually use for information electronics. Let's see, let me use the word information electronics. Electronics. So if electronics can be classified in these two areas, okay, when electronics adopted to convert and control power as power electronics, if electronics used to signal or information processing, and that's information electronics. In information electronics, the devices that we usually use are listed in this picture, including resistor, capacitor, magnetics, and semiconductor devices. Semiconductor devices could be working if in the analog electronic circuit, it could be working in a linear mode, as we all know. Or if you're talking about the digital electronic circuit, and then they are working under switched mode. This is the devices that we are very often using for information electronic circuit. And then specifically, if you're talking about information electronics in terms of integrated circuits, integrated circuits, IC. If all the information electronics you want to put them in one silicon chip, Then we would also reduce the devices we want to use, the type of devices we want to use, because we don't want to use an inductor and transformer. We don't want to use magnetic components. The reason is that in silicon chips, it's hard to integrate magnetic components. We can integrate resistors, capacitors, and transistors in ICs, but so far we're not able to integrate magnetics into silicon chips. Okay, and then in power electronics, the devices we're often using is a little bit different, quite different from signal processing. We want to avoid using of resistors, and we want to avoid using of semiconductor devices under linear mode. And you can imagine, after we have discussed the issue about efficiency, those are very easy to understand, because if we adopt resistor in power converter, the resistor is a power loss component. Okay. Also, semiconductor devices working under linear mode are also power lossy. Okay, we want these semiconductor devices working under switching mode. Under switching mode, the power losses on the semiconductor devices would be nearly zero, because you work like a switch. When the switch is turned on, the voltage across the switch is nearly zero. Okay, and when the switch is turned off, current flowing through the switch is nearly zero. So in either way, the power, because we know the power is always power across the switch is always equal to voltage multiplied by current. And if you have either one of voltage and current zero, then the power loss across this device is going to be nearly zero. Okay? That's the difference between the information electronics and power electronics. Okay, now let's move on to an example so that we can help you to recall many of the things you have learned before, both in power electronics course and in the control theory course. This example is quite simple, but it covers almost every issue we want to discuss. It is about a DC to DC converter. So that means we want to transfer or convert a specific input DC voltage, in this case is 100 volts. Transfer that 100 volts DC energy to the output, because the output requires 50 volts DC energy. This is very often happen in your real applications. Very often the input is at one level and the output actually requires another level. For example, in your cell phone, okay, cell phone right now basically uses a lithium-ion battery inside. When the battery is running at different state, the voltage of the battery is going to be changing. When it is fully charged, maybe at a very high level voltage. When it is using, and gradually the voltage of the battery will be declining to lower voltage. Okay, this is what happens from the battery in your cell phone. But the IC chips in your cell phone requires specific voltage level. They all requires like 1.8 volts, 3.3 volts, or sometimes even lower than 1 volts voltage. They require specific voltage level to be correctly running. So therefore, there is power converter between the battery and the IC chips to make sure the output voltage is really what you expect for the IC chips. So this is an example. Okay, input 100 volts, but output we want 50 volts. Suppose this load is a resistor with roughly 5 ohm. Okay, so then how do we design a DC to DC converter to meet that need? Okay, a very simple solution would be, okay, might be a high school student might propose a solution like this. We can put a resistor in between the input voltage source and load. How can we make sure this output voltage is exactly 50 volts? As long as this resistor we put in between is exactly equal to the load resistor. Okay, and then we know based on Ohm's law, okay, the voltage on the load will be exactly half of the input voltage, okay, and therefore half of 100 volts will be exactly 50 volts. That's a very simple solution. But obviously, as a engineer student at college level, you would be instantly find out there is a big disadvantage of this. What is the disadvantage? Power loss. Because this resistor in the power converter is going to be taking 50% of the input power consumed on this resistor, and only 50% of the input power transferred to the load. So the efficiency of this converter of this solution is only 50%. That's too low. That's too low. What else? Other than this disadvantage, anything not good? Anything else not good? Other than it's too lossy. Any other disadvantages? We are engineering students.
To control our output voltage will depend on the substitution of the resistance manually.
See it again.
I say to control our output voltage will depend on the substitution of the resistance, manual substitution of the resistance. We would have electronic control, like when we're using like a system.
Okay. So let's see. He actually mentioned one important issue. This is actually as engineer students. This should be very sensitive to you. The big difference between engineering and science, let's say, put it this way. What is the big difference between engineering and science? I would say one big difference is that science is always dealing with ideal case, theoretical case. But engineering is usually dealing with real case. Okay, in real case, this solution is not applicable. Why? Because in real case, there's always this thing which is called disturbance. science students, they usually didn't care about disturbance. But engineering students, we need to care about disturbance. This is real, because in the real world, there's always disturbance. The solution like this is only dealing with ideal case when, let's say, the load is exactly 5 ohm, or when the input voltage is exactly 100 volts. Then, if I adjust this middle resistor to be exactly 5 ohm specifically, then the output is going to be exactly 50 volts. But this is not going to happen in the real world. In the real world, there is nothing like this load to be always 5 ohm, not changing. In the real world, there's nothing like this. In the real world, there's nothing like this 100 volts input voltage. No. In the real world, there's always disturbance. The disturbance lies in the load. The load will always be changing with time. And time changing, load will be changing. Sometimes it's 5 ohm, sometimes it's 5.1 ohm, sometimes 5.2 ohm, sometimes maybe 4.8 ohm. That's real world. And then, in the real world, input voltage might also be changing. You can never have input voltage to be always 100 volts, not changing. Sometimes it could be 105 volts, sometimes it could be 98 volts. Somebody say I can have a very, very precise, very expensively controlled voltage source, but still, if you get into details, it's not going to be exactly 100 volts. It could be 100.0000001 volts, but not exactly 100 volts. And it's going to be changing this time. This is the real world. So as engineering students, we always have to keep in mind, we are dealing with real world, so therefore there's always one thing we have to deal with, which is disturbance. And there are two typical, and this picture actually shows, there are two typical sources of disturbance in engineering. One is coming from the load. Okay. When load are changing, light load, heavy load, that means this resistor is changing, it's going to be changing. That's one typical source, coming from the load. The other typical source of disturbance coming from source, energy source. Okay? So therefore, we need to handle, in the real world, the disturbance. And the way to handle disturbance is called what? In general, automation. Or automatic control. Sometimes people like to call that as automatic control. So as ordinary people, when they're not majored in this area, when they say automation, their understanding about automation would be something happen automatically and does not need to have some person to take care. That's called automation. But as engineering students, we should know the fundamental nature of automation is really to automatically handle disturbance. That's the fundamental nature of automation. Okay, so now, this solution, in order to handle the disturbance, as I say, as I said, one type of disturbance could be coming from the changing of load resistor. Another type of changing is coming. Disturbance may be coming from input voltage. So when they are changing, how can we be sure the output voltage, load voltage, is still exactly 50 volts? This is hard. This solution is quite hard to realize automatic control. Okay, so in the future, when if you want to identify whether a student is really an engineering student or not, then you ask him this question and see how what the answer he or she gave you. You can understand whether this is an engineering student or not. An engineering student would understand automation, the definition or the fundamental nature of automation is really how to automatically deal with disturbance. So this is not easy to implement automatic control. Somebody say, can I have, let's see, okay, we have learned control theory. Let's have some feedback control. I can measure the output voltage through feedback, and then after I measure that output voltage, I can adjust the middle resistance. It's also not easy to implement. How do you automatically adjust based on the measurement of output voltage to adjust that middle resistance? Not easy. It's doable. You can do that. You can maybe find a way, but too complicated and maybe cost too much. You finally probably need to have if that is a physical resistor, with a moving bar to adjust the resistor value, then you need a electric motor to adjust the moving bar of that resistor. Too complicated. So let's see some other solution. There's one solution like this. It does have feedback automatic control to solve the problem of the previous solution of being not easy to implement automatic control. This one is implementing automatic control. I'm not using a resistor in the middle. I'm using a transistor. And then, based on the feedback control theory, I measure the output voltage, from here, and then compare it with the reference value or commanding value. In this case, it's going to be 50 volts. I wanted that output voltage to be 50 volts. And the difference of that comparison is going to be used to adjust the base current of this transistor. Okay? For example, if output voltage is lower than 50 volts, lower than the expected value, then I adjust the base current to be higher or to be larger. Okay. When base current is larger, then this transistor is controlled to be having larger emitter collector current flow. When this current flow is larger, the current across load resistor will generate higher voltage. On the contrary, if the output voltage is already higher than 50 volts, this comparison will be generating negative difference. And that negative difference will be adjusting the base current to be a smaller value. When transistor has a smaller base current value, the emitter collector current will also be smaller. A smaller current on a resistor will be making a smaller voltage. So the voltage will be dropping as feedback, negative feedback control. So therefore, through this negative feedback control, we are able to handle disturbance coming from the load, if the load resistor is changed, or there's disturbance coming from the voltage, from whatever disturbance source, we can handle that. Through this automatic feedback control, we are able to control the output voltage at a specific value. And this really was implemented in engineering. Okay, I know some students, maybe they have used some. In Chinese, there is a chip which is called series regulator. Okay, if you have made some hardware electronic circuit before, and very often the power supply for that electronic circuit is actually formed through this three-terminal series regulator, like 7805. Okay, this is a kind of a chip supplying 5 volts positive up voltage. Okay, 7812, that's 12 volts voltage, something like that. Those are based on this. Okay, so this solution really can solve the problem of handling disturbances. Okay, realize automatic control. But what about the energy? What about the efficiency? If you look at the efficiency, then this is still bad. Why? Because this is 50 volts. Load has 50 volts. Input voltage is around 100 volts. So the voltage across the converter is roughly 50 volts. So this transistor will take 50 volts. On the other side, the transistor also has a very big current flow through. The current flowing through the transistor collector emitter terminals is the same as load current. Also around 10 amp. So this transistor is actually taking 50 volts at the same time 10 amp current. So the power loss on this transistor is 550 multiplied by 10, 500 watts. Exactly 50% of the input power is consumed by the converter itself. So the efficiency is still 50%. Too low efficiency. Okay. Then the real power electronics solution is like this. Remember, we want to avoid using resistor, avoid using transistor in linear mode. Okay. The previous solution over here, this transistor is working in under linear mode. We want the semiconductor devices to be working under switch mode. So there, we like switch. Therefore, we like switch. So let's see if we put a switch in between the source and load, and this switch is working. Has a it's called a single pole double throw switch. So therefore, this metal bar has two positions to put. It could be at position 1 or position 2. If we control this SPDT switch in a periodic manner, that means we control this switch periodically. And in every period, let's say the period is Ts. And in every period, we put switch at position 1 for some time. Okay, this is the time duration we put switch at position 1. In this case, when we put switch at position 1, the right-hand side voltage, Vs, would be exactly equal to 100 volts. Okay. And then for the rest of the switching period, I put switch at position 2. When I put switch at position 2, this voltage Vs is going to be exactly equal to 0 at this line. Okay, so therefore, the Vs voltage would be within one cycle, one period, for some time, same as 100 volts. For the rest of time, same as 0. And we repeat that control, okay, periodically. Next cycle, 100 volts, and 0, 100 volts, 0. So therefore, I got a square wave at Vs. Okay, and if I exactly put the duration of switch at position 1 for 50% of switching period, Ts. So that means for half of the period, this voltage, square wave voltage, would be at 100 volts. For the other half of the period, it's going to be 0. And if we do it in this way, the average value of this voltage would be exactly 50 volts. Average, if you take average over one cycle. Because half the time 100, half the time 0. Average is going to be 50. Okay? Therefore, how do we implement this idea? I put a single pole double throw switch over here, and if I put a low pass filter composed of inductor and a capacitor, okay, one inductor, one capacitor, to be composed as a low pass filter, then the square wave over here, after this low pass filter, is going to be only having DC value or average value at the output side. So it's going to be only 50 volts DC at the output side. AC components can be eliminated by the low pass filter. So this is going to be the solution. Okay. Look at this solution. We use switch, we use inductor, capacitor, no resistor. So therefore, the efficiency ideally would be 100%. Ideally, 100% of the efficiency. And you may ask, how do we realize this switch? That's power semiconductor device. We use a MOSFET, okay, and a diode connected in this way. When we turn on MOSFET, it's going to be exactly like the switch put at position 1. Okay. When we turn off MOSFET, there will be the current in the inductor will be freewheeling through this diode. It will be exactly like this switch connected to position 2. Okay. So a pair of semiconductor devices, such as a power MOSFET or IGBT, or together with the power diode, that will make this SPDT switch. Okay, and this is going to be very high efficiency. You can see inductor capacitor, they're not consuming any energy. Diode under switching mode, IGBT or power MOSFET under switching mode also consumes very small energy. So the efficiency ideally is going to be approaching 100%. So this is the solution, the power electronics solution we're looking at. Okay. On the other hand, we have feedback control. We need to measure the output voltage, okay, compare it with reference in the controller. That difference is sent to a compensator. Okay, a compensator therefore is going to be sent to a pulse width modulator to adjust the duty cycle. Okay. Duty cycle. Duty cycle of the control signal for the power MOSFET. Okay, that means we are able to adjust for how much time or for how much percentage of time over one cycle we are turning on power MOSFET. Okay, so therefore, if the output voltage is lower than the reference, the duty cycle will be enlarged. When duty cycle enlarged, this voltage, VS voltage, will be staying at 100 volts for longer time and staying at 0 voltage level for shorter time. So therefore, the average value of this waveform will be getting larger. So therefore, bringing output voltage increasing. On the other hand, if the output voltage is already higher than 50 volts, then this comparison will generate a negative difference. That difference will adjust the duty cycle to be having shorter position, a shorter time for MOSFET to be turned on. When the MOSFET has shorter time to be under on state, the voltage at 100 volts will be also maintained for shorter time, but longer time to be maintained at 0 voltage. So therefore, the average value is going to be decreasing. After low pass filter, the output voltage will be decreasing. Okay, so let's come back to the feed-forward feedback. Okay, now I know some students still have some puzzles on that. When we measure the output voltage and compare with command signal, then clearly you see through a controller like this, you can clearly see a formed closed loop. Okay, measure voltage VO, you measure it, VO, after comparing with reference, that's going to be it, flowing, that's going to be controlling the MOSFET, and then affecting the output voltage, form a closed loop. Okay, and then let me give you an example of feed forward. Okay, so let's see. Somebody said if there is a changing in VG, there's this disturbance coming from energy source side. I can measure that changing in VG. Let's see, I can have a measurement circuit over here. If I have measurement of VG and then the output of this controller, I have another controller over here. This output of controller is used to then directly adjust the control signal of a MOSFET. Okay, when VG is smaller, I adjust the control signal of MOSFET so that MOSFET is going to be turned on, maintain an on state for longer time. Therefore, I get an output voltage like this. This is let's say this is only 90 volts. Input voltage VG is getting smaller, only 90 volts. But when I detect that changing in input voltage, I change the duty cycle D so that the MOSFET is going to be on for longer time. Okay? Duty cycle increased. Then I can still make sure the average value, okay, of the output voltage to be still maintained at 50 volts. And when the input voltage is larger, let's say when the input voltage become 120 volts, it's not become bigger, I also adjust the duty cycle directly, adjust the duration of the time for the MOSFET to be under on state, so that that time duty cycle is getting smaller. And I can still maintain output voltage 50 volts. That's feedforward, because this signal, when you measure the input voltage through this controller, and the output of the controller is directly controlling the MOSFET and then controlling output voltage. That does not affect, this output voltage does not affect input voltage in return. There's no closed loop. Okay, you measure input voltage, and in the end, the signal goes to output voltage. There's no closed loop. This is feedforward. Okay, so this example is very often used to describe feedforward. But then it happens that in this case, the measurement